Good afternoon, and welcome to today's webinar, Optimize Ventilation for High-Performance Buildings, brought to you by Mitsubishi Electric Trane HVAC US. I'm Jessica Fiore, Managing Editor of Multi-Housing News. High-performing HVAC systems are always important in apartment buildings, and of course now during COVID, when ventilation is key to health and safety, they're at the forefront of everyone's minds. But with changing codes and sustainability concerns, it could sometimes be hard to keep up. Luckily, we are joined by some experts to help you with all your HVAC concerns. I'm joined today with Kevin Mitzkowitz, Senior Director of Vertical Markets at Metis, and Joe Sheffley, Senior Manager of OEM Applications at Metis, who will identify current industry trends driving specialized ventilation adoption, talk about efficiencies of variable refrigerant flow, and answer all your questions and concerns. Before I turn it over, I'm going to go over some housekeeping matters. First, we're going to be recording this webinar, and you'll be sent a link after the session. Also, Kevin and Joe are going to leave some time at the end to answer your questions. Please feel free to submit them at any time throughout the program using the dashboard on the right side of your screen. Okay, over to you, Kevin and Joe.
Thank you, Jessica. Good afternoon to everyone on the phone, and welcome to today's Optimized Ventilation for High-Performing Buildings webinar. On behalf of Joe Sheffley and the entire Mitsubishi Electric Trane HVAC US organization, I'd like to thank you for the time you've chosen to invest in today's session, and I trust that you, your colleagues, and your families are navigating these strange times as best you can. We're planning to spend the next 40 to 45 minutes discussing building ventilation, including the different styles and associated benefits and challenges, alongside how ventilation systems interact with variable refrigerant flow systems. The learning objectives of today's webinar include identify current industry trends driving increased ventilation adoption, understand the benefits and applications of ERVs, DOAS, and outside air units, all three terminologies that we'll get into today, examine the efficiencies of VRF technology, and provide an understanding of how highly efficient ventilation complements VRF systems for high-performance design. As Jessica mentioned, Joe and I reserve time at the end of today's webinar to address as many of your questions as possible. So be sure to submit them throughout the webinar using the Q&A function within the presentation software. HVAC systems, along with associated ventilation systems, can complicate the design or layout of a building. However, options do exist to avoid that complication. As building owners and developers of multifamily buildings, proper ventilation is crucial for occupant wellness and comfort. In addition, choosing an energy-efficient ventilation system can provide you with monthly utility savings. We'll get into more detail during the presentation and discuss options you can use when selecting the optimal HVAC and ventilation system combination. Let's start out talking through a few ways the needs of commercial buildings are changing throughout the United States. First, the population of our country continues to grow overall, while certain regions of the country are growing at faster rates than others. The growing number of baby boomers that are reaching retirement age is driving a population boom in warmer climates, such as Florida, Nevada, Texas, and the Carolinas. In addition, younger families in Generation X are moving to locations where jobs are plentiful or to the city of their choice as remote work continues to gain momentum. This has driven demand for affordable housing, schools, office buildings, and other retail establishments, all of which require ventilation systems in some way, shape, or form. Second, the rise of multifunctional spaces has driven the need for flexibility in design. Buildings are no longer built with one purpose in mind and may even have multiple purposes over the course of a single day. Examples of this include co-working spaces or buildings that incorporate a mix of retail and dining on the first few floors and multifamily living on the higher floors. In fact, the ability of a building to serve multiple purposes may even lead to the owner earning higher rents in the future. And lastly, the integration of smart technologies continues. Building occupants who have become accustomed to living in the information at your fingertips era are now seeking ways to personalize their comfort within an occupied space. Providing the ability to personalize occupant comfort through the introduction of smart technologies, such as app-based HVAC thermostats, leads to happier tenants, which makes your job easier. Let's take a few minutes and dive a bit deeper into some of the trends we just discussed and introduce a few new ones as well. A little earlier, we discussed the shifts in population that are occurring across the United States. These shifts in population have led to the construction of facilities to support that changing population, such as an increase in senior living facilities, hospitals, and multifamily housing across the southern United States. As it relates to ventilation systems, facilities such as the ones just described might require specialized ventilation systems, which are regulated by state and local codes developed from ASHRAE 62.1 and the International Mechanical Code. As ventilation systems become more regulated through new and improved code requirements, building owners are increasingly understanding the importance of IAQ to their buildings. The bottom line related to ventilation is that a greater awareness of indoor air quality and its impact on wellness is making commercial building owners and occupants take notice and demand solutions that introduce fresher air into a building. According to the California Public Utilities Commission, in a 2018 statement, quote, "The need for better performing HVAC systems will only increase as high-performance buildings become more prevalent due to ambitious sustainability goals set by private entities and state and local governments." The rise in high-performance buildings and their associated certifications, such as LEED, Green Globes, Passive House, Net Zero, and others, requires more efficient ventilation systems to be applied. Tighter building envelopes also require more sophisticated ventilation systems, specifically related to the area of occupant safety. Examples of these ventilation systems include dedicated outdoor air systems and energy recovery ventilators. The tighter the building envelope, the less indoor air can escape, potentially trapping harmful pollutants, bacteria, and viruses indoors. The demand for space-saving, flexible equipment has a direct correlation to the increasing demand for architecturally pleasing building designs. As building design becomes increasingly focused on style versus function, there is a demand for mechanical systems that are flexible enough to adapt based on those designs. In addition, the space-saving elements, such as the ability to decouple the ventilation and HVAC systems, a term that Joe will get into later today, enable the building owner and architect to design around their vision, while not impacting the engineering community, whose core responsibility lies in designing the optimal mechanical system to achieve the building's conditioning requirements. Lastly, ventilation system innovation has resulted in more compact designs, making it even easier to fit the right system into or on top of your building. The demand for energy-efficient mechanical equipment has been and continues to be a major influencer within the HVAC industry. With energy and other utility rates constantly fluctuating, you are probably looking to invest in efficient HVAC and ventilation technologies for your building. Whether through government regulation, sustainability concerns, market-based utility incentives, or just the desire to gain market share, the HVAC industry's key players have been ratcheting up efficiencies over the last few years. As we look out to the future, we thoroughly believe this is a trend that will continue to be at the forefront of product development for years to come. There's a demand for better control over mechanical systems within a building. Control over those systems comes at two levels: centralized and locally within the space. Centralized controllers can range from building automation systems that control all mechanical equipment within a building to controllers that control all aspects of one mechanical system, such as the HVAC system. Controllers within the space, including those that integrate smart technologies such as app-based thermostats, provide occupants the ability to personalize their comfort. Demand for both types of control, both centralized and local, continues to rise within the HVAC industry. Now that we've taken a look at trends within our industry, let's take a step back and briefly explore variable refrigerant flow, or simply VRF technology, before we dive into the ventilation-specific portion of today's presentation. VRF technology was introduced in the United States in 2002, after many decades of prominence throughout the rest of the world. Instead of moving conditioned air through ductwork to the space requiring conditioning, VRF delivers conditioned refrigerant directly to that space, eliminating the requirement for long runs of ductwork within a building. This minimizes the inefficiencies that come from moving conditioned air a long distance through those ducts and provides a more energy efficient, quiet, and flexible way to condition a space. When compared to traditional HVAC systems, this method of conditioning translates to life cycle cost savings for building owners and ultimately their tenants. VRF systems provide the ultimate personalized comfort experience for a building's occupants. Each space or zone requiring conditioning will have their own network of indoor units, which can operate down to 19 decibels, connected to an outdoor unit with refrigerant piping. This network of indoor units is controlled from within the space, providing the occupant with ultimate control. Due to the design flexibility of VRF, it can be applied to a variety of building types and applications. From adding capacity to an already taxed HVAC system on a college campus, to providing K-12 schools with a quiet, efficient way to cool classrooms, to conditioning a new high-rise multifamily building, VRF is the optimal HVAC choice. Lastly, some systems within the VRF lineup can cool some areas of a building while heating others from within the same system. This leads to happier tenants and fewer comfort control complaints for building owners and facility managers. The bottom line is that the efficiency of VRF systems, coupled with their ability to provide personalized comfort and ease of application into virtually any commercial building, has led to a rapidly increasing VRF adoption rate among specifiers. Now that we've discussed an overview of today's webinar, along with a look at VRF technology and a few points about the trends facing the HVAC and ventilation industries, we're ready to begin the ventilation-specific discussion. I'll now turn the presentation over to Joe Sheffley, Senior Manager of Applications for Metis, to dive deeper into the world of ventilation. Joe?
Great. Thank you, Kevin. Now that Kevin's given an overview of VRF technology and the market, let's take a look at ventilation and some of the products that we have available to serve this market. So first of all, why do we ventilate buildings? Well, for one, it's required by code in most applications. And that code is usually going to be International Mechanical Code or ASHRAE 62.1. It varies based upon your state and jurisdiction, but in most commercial buildings, it is required. Number two is really safety, indoor air quality, indoor environmental quality, IEQ it's called sometimes. But basically, as buildings get tighter and tighter, it's no longer safe when CO2 levels are building up because the building is so tight that there isn't infiltration from the outside like there were in buildings, decades ago. So safety is paramount. And that's why ventilation is regulated by mechanical code instead of energy code, is because it's really concerned with occupant safety, not with so much with occupant comfort and energy efficiency. However, number three here, energy efficiency is finally being brought to the ventilation market sector. Historically, ventilation was about occupant safety and having sufficient oxygen levels and indoor air quality. Now, efficiency via AHRI standard 920 is finally being brought to the ventilation market sector. So let's take a look at some equipment that is commonly used to serve these ventilation needs. So first we have an ERV, an energy recovery ventilator. An ERV recovers both sensible and latent energy, meaning that it exchanges not only temperature, but your moisture as well, your latent levels. So this contrasts with an HRV in that an HRV is sensible only, there's no moisture transfer. ERVs are typically used in light commercial and commercial applications, and they can be as large as tens of thousands of CFM. An ERV it recovers cooling and heating energy from what would be your exhaust airstream out of the building as you pull new fresh air in. And your average ERV is going to recover or take care of about half of your ventilation load in most applications. Now that's going to vary based upon your climate, location, application, amount of ventilation air, that sort of thing. So it's going to equalize not only temperature but humidity levels, and because filtration is integrated into every ERV you're going to find, it's also going to remove harmful pollutants. And the two main varieties of ERV that you're going to find, the one you're looking at here has a fixed plate core heat exchanger. There's also ERVs that utilize energy wheel technology. Okay, so moving on, continuing with ERVs, they help with a building's pressurization strategy. So if you look at the ERV on the previous slide, you can note that it has two different fans in it. One is a supply fan, one is an exhaust fan, and they can be controlled independently. So you don't always have the exact amount, you're not always exhausting from your ERV the exact amount of ventilation air that you're bringing in. And because of that, you may want to operate those fans at different speeds such that your building is neutral from a pressurization standpoint, or slightly positive is good if you're pushing out a little bit to keep contaminants out. And the reason that you wouldn't have the same air streams coming in and out is, imagine you've got a kitchen hood, some kitchen exhaust. You've got a few bathroom exhausts. Because that's already air coming out of your occupied space, that means your supply airstream needs to be higher, more CFM than your exhaust airstream. And so an ERV is going to take us closer to what we would consider room neutral air. And room neutral air we can define as somewhere in the 70 to 75 degree range, and of roughly 50% RH. Okay. So moving on from ERVs to dedicated outside air systems, or DOAS. These are typically commercial. They're not commonly found in too many residential or multifamily residential applications. What they do is they take 100% outside air, typically in the thousands of CFM, down to room neutral air conditioning. So if we're talking about a design day, 95 degree outdoor temperature, you're going to bring that 95 degree air down below the dew point in the 50 to 55 range, and then you're going to use hot gas reheat to reheat it to room neutral conditions, at which point you introduce that ventilation air to the occupied space as clean, fresh, room neutral air. And dedicated outside air systems, you're looking at a package system here. They also come in a split system variety. So inverter technology in general, if you've heard of VRF, if you've heard of mini splits, and the one thing they really have in common is that they're driven by an inverter compressor. And what an inverter compressor is, it's really just a variable speed, variable frequency drive that's applied to a specific type of compressor. So in a conventional air conditioning system, whether we're talking about ventilation or room conditioning, you're going to turn the system on. It's going to run at its one speed that it runs at. It's going to purposely overshoot set point, and then it's going to cycle off until the temperature rises in the space, and the cycle repeats once again. With VRF and mini splits in any inverter-driven system, it's going to more quickly reach set point, and then it's going to try to not achieve set point and cycle off. It's going to continuously run at a very low, quiet, and efficient point in the operation of the compressor. And also in some VRF systems, we call them heat recovery VRF systems. Kevin mentioned you can do cooling and heating from the same system at the same time. There is energy recovery in the refrigerant stream. So the energy performance of these simultaneous heating and cooling VRF systems is a step above and beyond a standard VRF system. If you look at the way ventilation was handled in the past, you're looking at a packaged rooftop unit here. So this system is going to provide the space, heating, and cooling, but it's also going to be handling the ventilation for the building, usually 20% or roughly in that ballpark for most commercial buildings. Now, the problem with this is because it has to juggle those two very distinct and different responsibilities at the same time, they tend to not do either one terribly well. And you also typically have to over-ventilate some of your spaces because you might have a conference room that requires 30 or 40% outside air, but then you've got your cubicle space, for example, in an office example, that only requires 15 or 20% outside air. But because there's only one way to mix it in this rooftop unit, you're typically going to over-ventilate those and provide 40% outside air for your entire building. So when you get to a dedicated outside air system ventilation design, the price point is going to be significantly higher, but you're going to decouple your ventilation from your space heating and cooling. So you'll have one system handling your space heating and cooling, typically VRF if you're dealing with a Mitsubishi system, and then your dedicated outside air system is going to be just what it sounds like, dedicated to the ventilation load alone. Here we have a newer product that's kind of relatively new to the VRF market. You can find this with multiple manufacturers, and what it is it's a 100% outside air fan coil that connects to the same VRF condensers that your space heating and cooling fan coils do that condition your occupied space. These are smaller in size than ERVs or dedicated outside air systems, and so they're typically going to be used for light commercial, maybe multifamily residential. And the neat part with these is that you're going to attach them to that same VRF condenser. You might have a VRF condenser that has 20 fan coils on it, serving your occupied space for heating and cooling, and then you might have 2 of these on that same system that are handling your ventilation. So now your ventilation and your space heating and cooling is all coming from the same VRF system with the same benefits of energy, performance, sound, equipment longevity and quality. And so you now don't have 2 dissimilar systems, one for ventilation and one for your space heating and cooling. So they are relatively small. If you look, most manufacturers are in the 300 to 1200 CFM range. If you get above that, you either need multiple units or you need to, step up to a dedicated outside air system or ERV or that sort of thing. So by connecting to the VRF outdoor unit, it's going to save energy on your ventilation, and it's also going to be a sole source supplier. You're going to have one manufacturer, one system handling both your ventilation and your space heating and cooling. It also offers you the opportunity for zoned ventilation. I mentioned with packaged rooftop units that sometimes you have to play to the least common denominator, and that if there's a conference room that requires 40% outside air, you may also have to provide that fraction to other spaces. Well, with zoned ventilation like this, you can have a dedicated unit for that conference room and then have a separate unit or units serving common office space with a much lower fraction of outside air. Let's look at some design considerations. So dedicated outside air systems, there's 2 basic ways to integrate them with your house heating and cooling system. It can be integrated directly, in the case of VRF, with the VRF system, or it can be separated out and completely decoupled. Now, when you integrate it with the duct system of a ducted VRF system, one of the problems you run into is that your design gets more challenging. You're going to have variable speed fans in your dedicated outside air system, and you're going to have variable speed fans in your VRF fan coils. And so your air balancing and assuring you meet your ASHRAE 62.1 minimum ventilation levels, it's a little bit more of a challenge in the field. And so what I was talking about here, you will see on the next slide, this is what it looks like if you've got the DOAS integrated with the ducted VRF fan coil system. So you're taking that room neutral ventilation air and you're feeding it to the back of a VRF fan coil that is conditioning the space. And so this might be 30% of the total volume that this fan coil moves is outside air, and the other 70% is return air. That would be your most common situation. But again, the fan balancing, the commissioning, this is a more cost-effective way to couple a DOAS system or to pair a DOAS system with a VRF system. However, it's just a little bit more of a challenge from a design standpoint and from ensuring your minimum ventilation levels meet code standpoint. So my personal preference is to decouple the 2 systems to have a dedicated outside air system that has its own duct distribution network and supplies room neutral air to all of your occupied spaces. Then this is refrigerant lines now from your VRF condenser to your VRF fan coils, and they are going to condition that space. So one of them is handling the ventilation load and a lot of the latent moisture removal load, that's the DOAS. And then the other system is making sure that it's 70 degrees in the space at all times, or whatever the set point is, desired by the occupant. So let's compare a full-blown dedicated outside air system design to the VRF 100% outside air fan coils. This is your typical design that you're seeing here, just a very basic layout of your average hotel or even a somewhat high-rise multifamily residential. You might have a left wing to the building and a right wing with an elevator shaft in between. Now, the elevator shaft typically is going to mean that you've got two dedicated outside air systems, one for each wing of the building, because a lot of times there isn't room to get the ducting back and forth, that sort of thing. So this is what you're going to find in your average, 4-story hotel. And so you'll have vertical ductwork, supply air ductwork coming down from your dedicated outside air systems and then teeing off at each floor to provide ventilation to each of the occupied spaces via grills, registers, diffusers in the ceiling. One of the shortcomings of this design is that cost. So you typically need to, these are large, several thousand-pound, these dedicated outside air systems are, and so they have to be rigged with a crane onto the roof many times. There's not a less costly or easier way to get them up there. And then also with this vertical ductwork, each time you tee off at a new floor, you need fire and smoke dampers in order to meet your code requirements for fire and security. So now if you look at the same building design, but we're looking at it with zoned ventilation, with lots of these smaller 100% outside air VRF fan coils, you're now actually going to eliminate the DOAS units that are still shown here. Those wouldn't be dedicated outside air systems on the roof. Those would be VRF condensers. And now, because we're going to have vertical refrigerant piping instead of vertical ductwork, we don't need the fire and smoke dampers at each floor. So the total building construction is more cost effective if you go this route. And so if we had shown the VRF condensers on the roof here, those might serve these ventilation fan coils, but then they might also serve VRF fan coils that are conditioning the space, not just the ventilation air. Let's take a look at efficiency. So there's a growing demand for energy efficient ventilation finally. So for years, I had said that at the beginning that ventilation was really about occupant safety and making sure that buildings are properly ventilated. Well, that's been pretty well established and is pretty well enforced by code and designed properly. And so we're finding that energy efficiency is finally making its way to the ventilation market sector of HVAC. And so introducing inverter compressors into dedicated outside air systems or into those 100% outside air VRF fan coils, you find if you just do an apples to apples comparison of a non-inverter compressorized system versus an inverter. And so when I say non-inverter, that could be a single speed scroll that's just on off. It could be a digital scroll with an unloader solenoid. Anytime you compare inverter to non-inverter, seasonally, over the cooling season, you're looking at about a 25% reduction in the energy cost. The energy input to an inverter-driven system is substantially less. And so in any of your areas that have high utility rates, that's going to make a pretty big difference over the life cycle of the equipment. The other thing that happens by having an inverter compressor, it's really just the nature of having a compressor that slows down. When it slows down, it's operating at part load or a fraction of its full capabilities most of the year. So when it slows down, you're not only saving energy, but it's getting quieter, it's less wear and tear on the system, and it lasts longer. It's really just, inverter compressors are growing in almost every market sector now because of their benefits. Okay. So when you put inverter-driven compressors in dedicated outside air systems, you get the option of retooling the refrigeration circuit, so to speak. If you look at your average digital scroll dedicated outside air system, if you've got, for example, a 10-ton 1500 CFM DOAS, you're typically going to have two 5-ton circuits. And so the coil will have two independent circuits The first one will be served by a digital scroll compressor with hot gas reheat. The other 5-ton circuit is going to typically be a single-speed scroll with no reheat. Well, when manufacturers are introducing inverter compressors into dedicated outside air systems, one thing that they're doing is eliminating the multiple circuits and incorporating one single circuit such that the amount of hot gas reheat you need is proportional to the cooling loading at any given time. What that means, or the short story, is that you're always going to have the amount of hot gas you need to get the air back to room neutral 70 degrees across all of your operating conditions. If you picture the system I was just talking about with a 10-ton unit with 2 independent 5-ton circuits and only hot gas on the lead circuit, when you're right around that midpoint of 5-6 tons, you might not have hot gas available, and so you could overcool the space and resulting in occupant comfort issues. Also, your inverter compressors, they're going to control more tightly than some of the other technologies, with the exception of digital scroll, which does a very nice job of controlling tightly. So looking at some multifamily residential applications. So it's the application that's going to dictate the ventilation solution. If you look at multifamily, in many instances, there is no ventilation requirement. If you have operable windows, you may meet your ventilation code per ASHRAE 62.1 or International Mechanical Code without any mechanical ventilation in the building. However, as buildings are getting tighter and tighter, Kevin mentioned net zero in Passive House and green globes and LEED. As buildings are getting tighter and tighter, the envelope's getting tighter, ventilation is becoming mandatory in almost all multifamily residential applications. Because the building is so tight, you're not getting fresh air infiltrating into your building, and so CO2 levels can rise, and it's no different than a commercial building at that point where you are concerned about occupant safety and indoor air quality. So getting back to what dictates the amount of ventilation that you're going to have for a given building, occupancy is one. If you look at an office, it's about 0.15 CFM per square foot. Blended rate. School is more like 0.3 CFM per square foot, or 30% of the fraction of supply air. And so it stages up as you get higher occupant density and as your occupancy style changes. When it comes to multifamily, it's typically a modest amount of outside air. It's typically 15% or less of the supply air volume of your space heating and cooling system. But again, things like climate, humidity, and building codes, it may vary from one region to another. Now, when you incorporate your ventilation air into a VRF system and you don't have a parallel ventilation system, like you don't have an ERV, you don't have a dedicated outside air system, when there's nothing separate but you still want ventilation air, you're typically going to want to limit that to maybe 10, 15% max. That number varies a little bit with your climate, but the whole point is that if you don't have a system dedicated to your ventilation, you could run into humidity issues because you're taking that raw, untreated ventilation air and expecting the VRF system to not only heat and cool the space, but to also pick up that additional ventilation load. Humidity increases the need for dedicated outside air systems. So when you're looking at an ERV versus a dedicated outside air system, ERVs are a fraction of the price. They're less complicated. There's less maintenance, all that. It's really your climate and your occupancy type that are going to dictate whether you go the ERV route or the DOAS route. And so as your humidity increases, dedicated outside air systems become more important to your design because you need to take that air below the dew point in order to wick out sufficient moisture to maintain 50% RH in your occupied space. In ERV, I mentioned, does sensible and latent heat transfer, so it is transferring moisture. However, it doesn't bring it below the dew point or do as much work or heavy lifting as a dedicated outside air system. And so if you look, the eastern 2/3 of the United States is really prime territory where dedicated outside air systems have great cost benefit for commercial buildings. If you look at the western third of the U.S., that's really ERV territory. You could use a dedicated outside air system, but why would you? It costs more, it's going to use more energy, and you don't need it because most places in California don't have the humidity concerns of the East Coast. So looking at the ASHRAE climate map here, this is a modified version of it that's simplified. You can really see that the moisture starts in the Midwest. I mean, if you're even in somewhere like Wisconsin, you still are in prime territory for dedicated outside air systems because those summers are hot and humid, even though you've got very cold, crisp winters. So it's really only that western third of the U.S. where you can get by with ERVs alone. It's really the eastern two-thirds of the U.S. where dedicated outside air systems. And when I say dedicated outside air systems, those could be packaged rooftop units like we showed for larger applications, or they could be the VRF fan coils that process 100% outside air, but basically just some sort of equipment that is going to bring the air below the dew point to condense out that moisture and create occupant comfort. And with that, I'm going to pass it back to Kevin.
Awesome. Thank you, Joe, for that detailed explanation of ventilation systems and how they're applied across a variety of commercial applications. Thank you to those that have already submitted questions. We've seen quite a few questions come through, and if you still have a question, be sure to submit it using the Q&A function within the presentation software. Joe and I are right on track to addressing as many of those as we can for you, and we look forward to that once we conclude our prepared remarks this afternoon. We'll now turn our attention to a few successful applications of integrating ventilation alongside variable refrigerant flow technology, focusing in on energy efficiency, occupant comfort, and the overall experience of tenants. The Distillery North apartments, located in South Boston, embody the values of the local community: arts, culture, and sustainable living. The 28-unit, 100,000 square foot complex was completed in February 2018 and follows the passive house model. The design team had a lofty goal of reducing energy consumption by at least 60%. To meet that goal and the strict passive house standards, the design team selected M-Series and P-Series systems from Metis. In addition to achieving passive house standards, their tenants also benefited greatly from the selection of these highly efficient HVAC systems. According to Fred Gordon, principal owner of 2nd Street Associates, quote, "For heating and cooling, we're talking $65 per unit per year." The selection of air source heat pump systems helped 2nd Street Associates achieve their passive house goals while delivering a huge win to their tenants when it comes to utility bills in their individual units. The next project we'll discuss is the lofts at Empire Yards Apartments in Macon, Georgia. When developer Brooks Patterson first came across a 120-year-old former ice and coal warehouse in Macon, he saw the opportunity for transformation. Brooks envisioned lofts at Empire Yards as a modern, multi-family property housing 28 units. Brooks set out to renovate the building's 65,000 square feet of space into loft-style apartments, while adding amenities such as a pool and rooftop patios. But the high ceilings that Patterson knew would be aesthetically pleasing to future tenants presented challenges when it came to choosing mechanical systems such as the HVAC system. Brooks ultimately chose ductless systems for the apartments due to their performance, quiet operation, and efficiency that came in a sleek package. Tenants were provided with the Kumo Cloud wireless control app, enabling them to control their apartment's temperature through a wall-mounted tablet or a phone-based app. In addition, tenants are achieving substantially lower utility bills because of the HVAC system. According to Patterson, quote, "Sometimes the monthly bills are as low as $45 per month in the wintertime." The tenants at lofts at Empire Yards enjoy year-round comfort, low utility costs, and convenient temperature controls inside their unit. Zone Comfort Solutions, coupled with ERVs and transfer fans, provided the answer to Patterson's needs. The last project we'll discuss today is 800 North High Street, located in Columbus, Ohio. While not a multifamily building specifically, this building has a lot of the characteristics of a mixed-use space that many multifamily buildings appear in today. The 10-story, 150,000 square foot mixed-use building was recently opened in the Short North Arts District of Columbus. It houses a restaurant, hotel, and co-working space in a pretty trendy neighborhood. Due to the conditioning needs of the diverse tenants, selecting an HVAC and ventilation system was certainly a challenge. The tenants demanded energy efficiency and all required differing levels of ventilation based on how their particular space was being utilized. The owners ultimately selected a VRF system along with a dedicated outdoor air system for ventilation. While this project really doesn't include 100% multifamily, it closely mirrors many buildings that we're seeing across the United States. These spaces, which marry residential, retail, dining, and other applications, are growing in popularity as young families move to the suburbs and yearn for the walkability they left behind in more urban environments. Before we jump into the Q&A, I'd like to leave you with 3 takeaways from today's presentation. First, multifamily buildings have had a range of ventilation requirements over the years, from simply opening windows to specialized mechanical ventilation. As tenants require higher indoor air quality and developers shift towards high-performance building strategies, mechanical ventilation will become a requirement. And finally, coupling VRF technology with ventilation systems promotes energy-efficient operation and cost savings for both the building owner and their tenants. That concludes the prepared portion of today's webinar. Joe and I have enjoyed discussing HVAC industry trends, along with an overview of VRF technology and a few successful examples of how VRF and ventilation systems tie together. We'd like to highlight 3 resources, among many others, which are available for your use after this presentation concludes. These resources include our company's website, metahvac.com, and links to our quarterly engineer, architect, and facility manager newsletters. In addition, we've included a link to access over 200 case studies on our website, including some of the case studies that we discussed today. On behalf of Joe and the entire Metis organization, thank you again for your time and your attention this afternoon. With that, I'll now turn the presentation over to Andy to begin our Q&A. Andy?
Thank you, Kevin. Thank you, Joe. Fantastic presentation, and let's get right to it. So the questions will vary from among people with different levels of expertise in the subject, so you're going to be addressing different levels. So I think that's okay.
Well, it's good, Joe. It's good because I have high-level expertise, and Joe has deep expertise, for those of you that couldn't tell. So we got you covered.
All right, great. All right, so let's start with number 1. Where is the fresh air coming from in the localized packaged DOAS units?
That's a good question in terms of system layout. So I know, Joe, you talked about a couple of different ways that you can apply ventilation systems into a building. What are some unique ways that you've seen of where we pull in fresh air to within a building?
Yeah, so I believe this question is in reference to the VRF fan coils that can process 100% outside air, and excellent question. And it's actually been a change in that your dedicated outside air systems on the roof, a vertical ventilation shaft has been the status quo for many years now. And so it's a little bit different when we start applying this product. Typically what you're going to do is you're going to have some sort of grill register diffuser and a filter combination on an exterior wall. And so now it's on the wall instead of the roof ducting down. This creates a couple of different challenges because you don't want to pull from an area where the air quality isn't good. If something else is exhausting in the close perimeter or close quarters to that, you also don't want something else that you wouldn't want to put it near where an exhaust fan is ducting out, because then you'll get short cycling, recircling of the exhaust air into the intake. So there's definitely rules about how far exhaust needs to be from the supply. But the short answer to the question is, in most cases, it's going to be some sort of grill, register, or diffuser with a filter combination on an exterior wall that's hopefully not in plain sight, maybe the back of the building instead of the front for aesthetic reasons.
Okay, great. Here's another one. So you mentioned ERVs with fixed plates. So what exactly does that mean?
Fixed plate refers to the heat exchanger, correct, Joe?
Mm-hmm.
Yeah, correct. There's 2 major varieties that ERVs come in. The most common one actually is going to be your rotating energy wheel. And so you've got air streams going in opposite direction, as the wheel rotates, it transfers heat and moisture. In a fixed plate, you've just got a block or a core where there's a channel going in one direction, that might be your exhaust air, and then a channel going in the other direction, supply air, and the streams of air cross indirectly through the membrane of the fixed plate core. It's the same process that's going on in an energy wheel. There's just no moving parts, and so there's less stuff that can break. They also age very well in that they can be cleaned as much as 10 years later and brought back to 99% plus of their original efficiency. So there's a lot of benefits to a fixed plate core. They do take up a little bit more size than an energy wheel. So when you talk about your cabinet, an energy wheel is often going to be more cost effective because you can shrink your cabinet size, and cabinet size is king when it comes to price per CFM or ton.
Okay, great. All right. So in what areas of the country are energy codes requiring more energy efficient ventilation?
And energy efficiency within, as we touched on, within the HVAC industry is becoming one of the big issues on the minds of all manufacturers. I think you're seeing a lot of it in the major cities. Joe, if you look at cities like New York, which is pursuing strategic electrification initiatives, and some cities out on the West Coast, are there any that stick out in your mind in terms of where codes and standards are pushing energy efficiency?
I would say it's more or less national. I mean, you're going to find areas where they're pushing for above the minimum, code standard requirements. But you've got two major standards that govern ventilation. So for our ERVs, we're looking at AHRI Test Standard 1060. And so that is a test standard that anyone that manufactures an ERV for sale in the U.S., they have to test it for not only the sensible heat recovery, what percentage it is, usually they're in the 70s, and what latent or moisture removal percentage you have, usually those are in the 60% range, but you also have to test for what is the pressure drop through that fixed plate core across the energy wheel, because that translates to fan energy. So for the longest time, ERVs have been regulated from an energy perspective. It's just that any of your dedicated outside air systems or your systems that have mechanical heating and cooling, those have not historically been regulated. And what happened is just this year in 2020, a few months ago, AHRI published a new test standard called AHRI 920. And what 920 does is it is for 100% outside air systems, but also it governs high fraction outside air systems. And it introduced new efficiency metrics. So if you're familiar with EER, for example, that you would see even on a window unit, that you get from Home Depot, that's energy efficiency ratio. That's your full load cooling efficiency for a space heating and cooling system. Now, this new test standard 920 has MRE for moisture removal efficiency. That's your full load cooling efficiency of a ventilation system, of a DOAS. And then they've also added ISMRE for integrated seasonal moisture removal efficiency, and that's your seasonal energy performance. And so the standard is not yet in effect. Once it gets published, there's usually about a 1-year cycle to give the manufacturers time to test to the standard and publish in the AHRI directory. But if we're having this conversation this time next year, you'll find that dedicated outside air systems and high fraction outside air systems will have efficiency metrics published in the AHRI directory, which is ahridirectory.org, if anyone isn't sure where to find that, and that will be readily available. Now, with that said, that was more from a test standard equipment standpoint. To Kevin's point, you'll find areas of California, New York, Massachusetts, where they are getting more focused on filtration and ventilation quantities, that they're even asking to go above the minimum codes and standards.
Okay, great. Next question. Can you describe the maintenance of these systems for multifamily buildings? So I'm presuming they're talking about DOAS and ERVs.
Yeah, maintenance is certainly a topic that's on the mind. I'll speak briefly to VRF before I toss it over to Joe for the DOAS and ERVs. From a VRF perspective, that's something that I did not touch on in my remarks is maintenance. maintenance is certainly and was certainly at the forefront of the initial design process for these systems many years ago. Really, it comes down to periodic filter changes and cleanings every quarter typically. Or you want to make sure you get on the roof and check the electrical connections and clean off the condenser coils outside. But really, maintenance is one of the hallmarks of a VRF system in terms of the minimal maintenance that needs to be done and minimal specialized maintenance that needs to be done. Typically, a maintenance technician within a building or a facility manager can do most of the maintenance work themselves. Obviously, if you're going to get into refrigerant and refrigeration cycles, you want to make sure you're working with a licensed mechanical contractor. But any of the basic maintenance of filter cleanings, even a tenant can take a filter out of an indoor unit and clean it, a washable filter, and put it back in. So very minimal maintenance when it comes to these systems. I know, Joe, on the ERV front, the systems we work with are fairly easy maintenance. Can you give kind of an overview of maintenance when it comes to DOAS and ERVs in general?
Sure. So for an ERV, you basically got 2 fans and a heat exchanger in a box. And so keeping that heat exchanger clean means you're going to be changing the filters or cleaning the filters depending on whether they're washable or replaceable. And then also sometimes if you have a core or a wheel, the actual heat exchanger itself, you can vacuum it with a soft bristle brush attachment for a vacuum cleaner. And so it's not something that's done routinely. The routine maintenance on an ERV would probably just be changing the filters. And then after several years, you might actually clean the heat exchanger core or wheel itself. So really minimal. I mean, like Kevin said with VRF, keep the coils clean and change your filters. That really is your maintenance on a VRF system. On an ERV, it's even less because there's no mechanical cooling coil or anything. So it's really just keeping the filters clean. If you get up to a full-blown dedicated outside air system, however, there's a lot going on there. You have dampers. Those dampers need to be greased to make sure that they're not drying out at the joints and breaking. You've got your energy wheel, which has the same maintenance of any kind of ERV. You've got coils inside of the cabinet and outside. Both of those should be kept clean. There's VFDs in the system that should be checked periodically to see that you're getting the proper airflow over time and as the filters load. So that there's a lot going on in a dedicated outside air system because there's just a lot of mechanical equipment in there. So those are a little bit heavier on maintenance, but yeah, ERVs, change the filters, VRF, clean the coils and change the filters, dedicated outside air systems, a little bit more involved.
Okay, I'm going to combine 2 questions because in part they're asking the same thing. So can you retrofit a multifamily building with VRF systems in either a DOAS or an ERV? And then another part, someone gets more specific and asks, could you retrofit a 30,000 square foot 2-story office building that's currently served by 2 package units with these systems?
Yeah, the short answer is yes. One of the benefits of VRF technology and quite frankly how it got its start in the U.S. market was retrofits. We have a lot of existing buildings when the technology first came here in the early 2000s, and retrofits, especially in the northeastern United States, was really its leap to prominence. With the refrigerant piping versus ductwork and the flexibility of the technology, retrofits is a great way to go. Joe, from an application standpoint, I would presume that with these applications and others, you'd want to make sure you're playing within the confines of what exists and then making sure that you're not inadvertently doing something too costly if ductwork already exists, for example.
Yeah, so to Kevin's point, it's going to vary from building to building, even for the same occupancy type. Like not every office is going to be the same when you look at it from a retrofit standpoint. However, this is one area where VRF really shines. It's a technology that you can install without, you don't necessarily have to have major renovations to your building to accommodate it. Typically, you're going to be coring a 3-inch hole for your refrigerant lines with the insulation wrapped around them. So anywhere you can core a 3-inch hole and run your piping, that really is going to offer you the flexibility to add a VRF system. Now, typically, they're going to be inside the walls, and so it's always better if someone's doing a major renovation rather than a straight retrofit. And to Kevin's point about your price point and whatnot, if you've got, say, a building with 7 packaged rooftop units, a duct distribution network, and they're nearing end of life, it's never going to make sense in that particular application to put a VRF system in, because you've already invested in all of the ductwork installation and the interior of the building. It's going to make sense to drop 7 new rooftop units in the place of the old ones with a curb adapter. It's just because the distribution system is already there. So anytime you have to install a new distribution system, your price point is not great. So think of the VRF system. You don't just have to install a new outdoor unit and indoor unit like that rooftop. You just have to drop a new one. You also need your pipe distribution network to move that refrigerant. And so that's where your price point just gets ugly if there's already a viable existing distribution system.
Okay, great. So this next person says, I've heard people talk about how VRF outdoor units are quiet, but what about adding these ventilation systems? What kind of noise levels could we expect if we have VRF outdoor units and one of these ventilation systems?
That's a timely question as we think about rooftop patios and other amenities within some of these mixed-use spaces that we had talked about. And really, Joe, I presume some of that goes to application, what equipment is needed and where it's located, but also what options that somebody might choose.
Sure. I think that one of the best features or value to the market, to customers with adding this 100% outside air VRF fan coil is that it's the same technology. The sound attributes are going to be identical to if that fan coil were conditioning the space. So your ERVs are going to be quiet for the most part. Almost everyone has the option for an ECM or DC fan motor in there, which are super quiet. And then the VRF fan coils that are dedicated to ventilation, those are going to be the same sound attributes of VRF. The only place where it might get tricky is if you've got large dedicated outside air systems and you don't have an option for an inverter compressor. The digital scroll compressors are they're great from a performance standpoint. They're not good from an energy standpoint, and they're really not good from a sound perspective. And so if you've got the option, if you're already laying out a VRF system or a mini split system, I'm always a big proponent of pair that with the same technology. If you're going to choose a DOAS to go with that, make sure you've got the inverter compressor in there, because you don't want a really quiet, efficient system next to a very noisy, inefficient system on the same project. It's usually good to have nice agreement and meet customer expectations.
Okay, 1:57, so might not have much more to go. So here's what's better in your opinion: a naturally ventilated building in areas where it's allowed with some energy loss, or a highly insulated building with an expensive mechanical system?
I think that really depends on a number of factors. An application, it could be the use of the building, it could be what the owner is trying to promote to their tenants. And Joe, I'll toss it over to you. I think this will probably be our last question given the time, but can you take us into your thoughts on that from an applications perspective?
Sure, that's a really good question. And just in terms of natural resources and the impact on our environment, if you can have a naturally ventilated building and have the same indoor environmental quality as a mechanically ventilated system, I guess I would say go to the direction of naturally ventilated, because it's so much better for your global impact. I think the reason that we typically have to go to these mechanically ventilated systems is because you can't achieve that level of indoor air quality, or as soon as your RH is above 60% for more than 72 hours, mold can grow. And so if you can't maintain those, indoor air quality, those same parameters with a naturally ventilated system, well, then it's almost like it forces you into mechanically ventilated just for occupant comfort, safety, and air quality.
Awesome. Well, Joe, thank you, and Andy, thank you. I'll just offer a quick comment here before we wrap up to make sure we hit our time limit. Again, thank you to everybody that joined us on the phone today, and especially to Joe for for helping me with this webinar, and Andy for asking the questions. We hope you took something away from today. If you do have any other questions or want to have a follow-up discussion, please don't hesitate to reach out. We're happy to help you in your pursuit of the most energy efficient and comfortable buildings for your tenants. Thank you very much, and have a great afternoon.